Hi, hello everybody. Welcome to the second episode of France's AI Talks. We'll wait a few minutes before starting the session as we are expecting quite a lot of people today. The session today, I think, had a tremendous success, which is great news. A lot of people will connect in a few minutes. So stay tuned. We'll start shortly. I'm seeing a lot of familiar faces connected. This is pretty amazing. A lot of startups, a lot of researchers, large groups. I see that you're getting familiar with the chat. From what I'm seeing, I think researchers are mostly represented at the moment. We have some Facebook people, AXA, Capgemini. That's pretty cool. INRIA. Welcome, everybody. Stellantis also. École des Ponts Paris Tech, welcome. Cardiologues, very cool startups. All right, I think we can kick off now. So hello again, everybody. Welcome to the second episode of France's AI Talks. I hope you like the previous one. You know me now. I'm Julia. I'm head of European Affairs at France Digital, and I'm the lucky coordinator of our AI task force, which gathers now more than 70 startups. And happy to see, that many of you are connected here today, a lot of amazing participants. And to quickly present the association, to quickly present France Digital, we are the largest startup association in Europe. And every year we organize France's AI conference in Paris, together with the Paris Artificial Intelligence Research Institute, PRAIRIE, together with Isabelle. Last year, we had more than 70 speakers here in Paris, 2,000 participants, and we also organized the biggest matchmaking track between startups and investors. It was a terrific event, really nice, and that's why we thought that it would be great to continue this initiative. That's why we are here today. We are really thrilled to continue this collaboration with PRAIRIE and to launch France's AI Talks. So stay tuned. We will return here every month for exclusive talks with renowned researchers living abroad with a French touch. And together here with the whole ecosystem, I see that you're a lot of people connected from the ecosystem, researchers, startups, industry. Welcome again. 2 important details. If you want to tweet, you know what to do. Use hashtag FranceIsAI, hashtag Prairie, and at France Digital. I'll write it down for you in the chat. And also, please do participate. Use the chat, use the question feature here on Livestorm, and we will address all your questions and comments at the end of the session. We'll have a dedicated time for a honest and direct discussion with you all. So please do use these features. And without further ado, I'm really happy to give the floor to Isabelle Riel, Director of PRAIRIE, who will interview our special guest, Yann LeCun.
So thank you, Julia. As you, I'm pleased to welcome everybody here today for the second France's AI Talk. The next one will be given by Aude Oliva from MIT on April 7. You can put it on your agenda. But today we are very proud to welcome one of the stars of AI in the world, let's say Yann LeCun. Yann is now Vice President and AI Chief Scientist at Facebook, Silver Professor of Computer Science, Data Science, Neural Science, Electrical and Computer Engineering at New York University. He's ACM Turing Award laureate, member of the US National Academy of Engineering. He was also professor at Collège de France in 2015. And I would also add that we would like to thank him for having supported PRAIRIE from the very beginning. So thank you, Yann. So as Julia said, you have on the right of your screen a place for question. You can write question and vote for question. We will try to have all of them at the end of the session. So just to introduce you, Yann, some personal question about you. Where did you study? What is your career path?
So I grew up near Paris in the northern suburbs, and I studied at ESIE, ESI2E, ESIE, which is now part of Université Gustave Eiffel in Marne-la-Vallée. But at the time, it was an independent school that was under the aegis of the Chamber of Commerce of Paris in the 15th arrondissement in Paris. So this was on in Paris, and it moved when I left. I then did a DOA, there were no M1, M2 at the time, at PRAIRIE-PSAI, and then a PhD, doctorat at PRAIRIE-PSAI. My advisor was a gentleman by the name of Maurice Milgram, and then I went for a postdoc in Toronto, and then a year later at Bell Labs, but you'll hear about this in my talk because I'm going to talk a little bit about my personal experience.
Okay, thank you. So just something, a very personal detail. Can you tell us about some special milestone, an opportunity, a regret in your career, something?
My regret is not to have been able to do this career in France. That's my biggest regret, really.
It's a very good answer.
I mean, I went to Canada for a postdoc with the idea of coming back. I was recruited by Bell Labs when I was a postdoc in Toronto, so I stayed in Toronto only 1 year. And then I went to Bell Labs with the idea of staying 1 or 2 years and then going back to France. And I did come back to France, but I only stayed in France 6 months, and then I went back to the US. And so I'll tell you a little bit about why this happened. But I wish I could have done my career in France or come back. The thing is, there is a point where you expatriate yourself and you build your life. Your children grew up in a different country and they don't want to move back. They don't want to move, right? So you can't move anymore, right? There's a point where you're stuck, essentially.
Okay. So anyway, we have you today with us in France. So I give you the floor for your talk.
Okay, so I guess I'm sharing my screen. All right, you should be able to see my screen, right? I hope this works.
Very nice.
All right, okay. So this is going to be a whirlwind tour, and the talk I've prepared is much longer than what it should be. So I'm going to skip a lot of it. Don't be alarmed. And some of it is going to be personal history. Some of it is going to be about how research how research is kind of handled in the US, and the different types of opportunities that we can find in the US versus Europe. And also how research is organized, and also kind of the topic of research itself and where I think AI is going in the future. I hope I can get to that. Okay, so you go back to the early history of AI, and even in the 1950s, when Turing wrote about his famous paper on AI, which was really a philosophy paper, he talks about the fact that it would probably be a better idea to build an intelligent system that could learn than to build it from scratch as the mind of an adult, right? And so that's kind of, the idea of machine learning was there, but of course not the way to do it at all. The way I came to machine learning was I was an undergrad, so I was studying electrical engineering at SEA, and I've seen some friends here who are from SEA, so they know what I'm talking about, and who were there at the same time actually. And I was interested in AI already, but it wasn't really kind of a field that you could study, and there was no such field as machine learning that you could study at all. But I stumbled on this book, which was a debate between Noam Chomsky and Jean Piaget. Noam Chomsky, the famous linguist, and Jean Piaget, the Swiss developmental psychologist. And they were debating the nature-nurture debate, like is language acquired or is it innate? What is acquired, what is learned, what is not learned? On the side of Piaget, so on the side of learning, was a gentleman by the name of Seymour Papert, who came from MIT, and this debate took place in the late 70s, and he was singing the praise of a model called the perceptron. And so I read about this, and the perceptron was a machine that was capable of learning, and Papert was describing it in glowing terms. And so I said, a machine that can learn, I find that really amazing. So I spent all of my free time at the INRIA in Rocancourt, actually, at the library, basically going through the old literature on the topic of perceptron and learning machines and statistical pattern recognition and things like this. I was absolutely fascinated by the topic, and I did this while I was an undergrad. I started when I was in second or third year of engineering school after high school. And I learned about the history of how people started to think about intelligent machines and getting inspired by neuroscience or not, and the early days of computer science. And so basically it started with cybernetics, Norbert Wiener, and earlier with people like McCulloch and Pitts, who proposed the idea that if neurons are binary elements, they're basically threshold gates. You can use them to build logic circuits, and with this you could get machines to reason. So perhaps the brain works, the reasoning in the brain works because neurons are logical elements. Okay, so that was kind of an interesting idea. The psychologist Donald Hebb had this idea that perhaps, of course, people knew that learning probably was due to synaptic plasticity between neurons, but he proposed this idea of Hebbian learning. And then a few years later, in the late 50s, Frank Rosenblatt came up with the perceptron model, which was sort of a classifier, the first linear classifier, if you want. And we don't realize that today, because you can write the code for a perceptron with 3 lines of Python today, or even 1 line if you really insist. But back then, you actually had to build a physical machine. So the perceptron is shown at the bottom here, with Rosenblatt holding a module with 8 physical weights. The weights were actually potentiometers with buttons on them that were actuated by motors. There was no kind of digital computer that was powerful enough or simple enough to use to actually do this. So we implemented this as an analog computer. So simultaneously, people were thinking about AI in other ways, kind of coming from the top, and then kind of trying to reproduce logical reasoning, problem solving, and things like this. And that's where things like the Lisp language and the general problem solver and chess players and things like that came out. Arthur Samuel, though, was an interesting guy. He was working at IBM, and he built a checker player that used tree exploration, which is kind of classical, which became then sort of classical AI, if you want. But he also actually devised a system by which the system could be learned. It was kind of very similar to reinforcement learning. So this is the early ancestor to things like AlphaGo and things like that, if you want. So that's kind of it's kind of a fascinating history, and what happened, which I discovered, was that Papert wrote a book in 1969 that he co-wrote with Marvin Minsky, also from MIT. That book was titled Perceptron, and so this was 10 years before the debate with Chomsky and Piaget. And that book actually killed the entire effort of the perceptron. So what happened in the late 60s is that people stopped working on machine learning, essentially. They stopped working on this idea of that you could build intelligent machines by getting them to learn. So the branch that was kind of logic-based AI kind of continued. There was no learning there, or very little. But sort of the more kind of machine learning-based AI kind of disappeared from from research in the West, including in Europe. But it subsisted somehow in Japan. Japan had a slightly separate ecosystem for research, and the people like Kuniko Fukushima and various others who kind of kept working on neural nets when nobody else in the world was doing it. So when I started kind of getting interested in this in the early 80s, the golden age of AI was was the golden age of expert systems, really, kind of logic-based AI, which was completely separate from machine learning. Nobody was talking about machine learning. But I learned pretty soon, by more or less by accident, that a few people actually were working on neural net models, and there were people who were not actually connected with computer science. They were either psychologists or physicists, and sometimes cognitive scientists, but the name didn't exist very much. And so I suddenly realized there were people in the world who actually were interested in the stuff I was interested in at the time, and I couldn't find anyone who was interested in it. There were a few people that I met at an independent lab called LDR, Laboratoire de Dynamique des Réseaux in Paris, with Françoise Soulier-Faugelman and Gervais Bush and various other people. And they were interested in automata network, and they connected me with that sort of new community of people who were getting interested in neural nets. And because those people were physicists and or hardware engineers and cognitive scientists, they didn't care about the fact that computer scientists and analytical engineer would not actually care, would not touch the perceptron, because it had become a sort of a bad word, if you want, like to work on this. But there was kind of something that survived, which was a field called statistical pattern recognition. And statistical pattern recognition was very active in the 70s, and that was sort of the descendant, if you want, of early work on the perceptron and similar models. Now, as you know, it happened very often in AI. Things kind of died in the late 80s. Expert systems kind of didn't really fulfill their promises, and it became considerably less popular. And the backpropagation algorithm and multilayer network appeared, a little earlier, and that sort of took off. There was a big wave of interest in those things. So in the late 80s, early 90s, there was a wave of interest in neural nets, and that died in the mid 90s again. And the reason I'm telling you this is because it's kind of relevant to things I'm going to tell you about later. So there was kind of a dark period of about 10 years between the mid 90s and mid 2000 where nobody really was working on neural nets. But machine learning took off. So there was a lot of very interesting progress in machine learning, just not using neural nets. And then it started again in the late 2000s, essentially. We saw the kind of revolutions we've seen with deep neural nets and deep learning and things like that, right? What's happening now, which I'll talk about at the end, is kind of perhaps a new era in deep learning, which is brought about by a new paradigm of learning that I call self-supervised learning. So this is sort of going beyond the traditional model of supervised learning and as well as reinforcement learning. Okay, so supervised learning is really sort of the workhorse of of machine learning today, and most applications really are forms of supervised learning. And we all know what it is. You tell the machine the answer you want, and you adjust the parameters of it so that it does what you want. And that led to the standard model of pattern recognition from the 1960s and 70s, where, and even much later, until the emergence of deep learning, really, where you take an input, you feed it through a hand-engineered feature extractor that produces a good representation, and then you plug it to a trainable classifier, very often a linear classifier or something like a supervector machine or nearest neighbor or naive Bayes or something like this. And you can find all of this in the famous book by Duda and Hart in 1973. So why was there a neural net winter in the late 60s? And I think it's interesting to think about this. Why is it that people moved away, that the perceptron book basically killed the whole effort? There's two reasons. There was a lot of hype. Like there is some hype today, but there was a lot of hype at the time on the potential of those learning machines, which of course they were very limited because they were limited to single layer essentially. And people didn't figure out things like backprop. So they knew that the salvation was in building multi-layer systems, but they didn't know how to do it. There were several proposals that were not, none of them were satisfactory, really. And the main reason for this is, first of all, there's, computers were not powerful, blah, 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 things like that. But also they had the wrong neurons. So they were using binary neurons. And when I started working on this in the 1980s, I was using binary neurons. And if you have binary neurons, you cannot even think about backprop, because backprop requires differentiable functions. So in fact, the community kind of didn't think about backprop, which is really a practical application of chain rule and should be completely obvious, because they were using binary neurons. And it took so long for people to figure this out. And why did it take so long to figure this out? It's because if you have binary neurons, when you write a program to compute the output of a neural net, you don't need to do multiplications, because since the output is binary, you just need to add or subtract. You don't need to multiply anything. And at the time, the hardware was so inefficient that doing a floating point multiplication was really expensive. So if you could just do additions, furthermore fixed point additions, you could run bigger neural nets than if you had to do floating point multiplication. So efficient floating point multiplication didn't appear until the late 80s. So people didn't think of using sigmoids and things like this until then. But the appearance of backpropagation, Hopfield nets kind of made the topic, how would I say, respectable again through physicists, and then backprop appeared at that moment. And I had a little bit to do with this, but I worked on backprop, but my first version of backprop was actually using binary neurons as well. I'll come back to this in a second. So, I mean, the reason why you want to have multiple layers was obvious, back to people in the 60s. So it's not like this was something that people didn't think of. They just didn't know how to train a system with multiple layers. But it was obvious from, intuition, from engineering, from work in neuroscience that, vision was a hierarchical process, that, in the brain, kind of the visual recognition process goes through multiple layers. And if you want to reproduce the visual processing machine, you had to go through this. And so that really what deep learning is all about in the end. It's stacking multiple layers so you can train a system to basically have apply a sequence of nonlinear transformations to your input. So this idea came from neuroscience, from classic work in neuroscience on the structure of the visual cortex by Hubel and Wiesel. This is Nobel Prize-winning work, so it's not obscure at all. But a work that was at the time more obscure is by Kunihiko Fukushima, who in the late 70s, early 80s, came up with this model called the cognitron and neocognitron. And it was basically trying to build a computer model of the idea that Hubel and Wiesel proposed were the underlying structure of the visual cortex. He didn't have backprop. This was, the early 80s. So he didn't train his system using backprop. He used basically a local competitive clustering-like algorithm. But he had the idea of having local connections and shared weights, okay? Where you can replicate a feature detector over an entire field. And he had the idea of complex cells, simple cells, pooling, essentially, things like that. So he built this thing. It was very slow on his computer, and he had the last layer was basically a perceptron, right? So you could train that supervised. And he had several versions of this. So this was really pioneering work. And I was really inspired by that work when I started working on this. And I started building, when I was still an undergrad, and when I started my DOA or my PhD, I started building networks of this type, which I didn't know how to train either. I had this idea that perhaps, there would be some signal going backwards to kind of train those systems to do the right thing. But again, I was using binary neurons for computational efficiency reasons. And, you don't come up with the idea of backprop if you use binary neurons. So the idea that I came up with is to propagate targets. We actually call this now target prop. It's actually kind of a form of, there's a limit case in which it's equivalent to backprop. But basically, the signals I was propagating backwards in my system were virtual targets for every neuron. It was kind of, a bit challenging to write this on, in Fortran on, slow and big computers, and there was no data sets you could collect. There was no internet, so a little challenging. And I came in, and there was very few people working on this, so it was, there was no email either, right? So it was difficult to communicate. This was all by regular mail. In 1985, early 1985, the people I was in contact with in Paris, Françoise Feugelman-Soulier in particular, organized a workshop in the French Alps, where she invited all the people who were working on this domain from around the world, and they all came. A lot of physicists and people working on, like Terry Sinofsky, who was working on Boltzmann machine. He was really the guy I wanted to meet. People from Bell Labs, Larry Jekyll and John Denker, they were building basically hardware neural nets because John Field was also at Bell Labs. And then neuroscientists like Jean-Pierre Changeux, Christophe van der Masburg, etc. And the question, in this workshop was, can the brain be analyzed with the tools of statistical physics, essentially? And that turned a lot of physicists into neuroscientists. But that's where I kind of met the community. In particular, I met what will become, my colleagues at Bell Labs. But then, to tell you a little bit, how things were kind of a little complicated. By 1985, it was clear to me that I kind of came up with the idea of backprop, and then I met Jeff Hinton and everything. So the idea of backprop was kind of in the air. It wasn't published yet, but it was in the air, and so I implemented it and experimented with it for sort of various applications, which were kind of the main topic of my PhD, really. And this was licensed to industry in France, actually, so it was used by several companies inside France in the mid 80s. But it was very painful, and a new community was being created, and it was a little bit people who were kind of really very much at the periphery. So you see at the bottom here, Jeff Hinton, Terry Sinofsky, Jay McClellan, Derry Turetsky, people like this, and then a bunch of students. I was one of them because I'd met Jeff and Terry before. And those basically were young versions of people who are now very famous in the domain, like, for example, Stan Dehaene, Mike Moser, Michael Jordan, people like that, and Richard Durbin, who's does bioinformatics. So this summer school, which was at Carnegie Mellon University, actually created the first real community of people interested in neural nets. This kind of jump-started the field, really. That had like a huge impact on me, certainly, and a lot of people. Now, I was finishing my PhD, and I needed to basically experiment with sort of bigger neural nets, and I'm going to tell you a story which I think is relevant for today. It has some relevance for today. I met with someone that many of you know called Léon Boutou, and he's actually now a colleague at Facebook, but at the time he was finishing his studies at École Polytechnique. This was in early 1987. And he and I worked together. He for his end of study project at École Polytechnique, and me in the last year of my PhD. We decided to write a neural net simulator together. And this is a system called SN, and there was no Python or nothing like that at the time, so we had to write our own interpreter, which was an interpreter for the Lisp language. It was derived from a Lisp language at the time called Le Lisp. It was very popular in France. And we implemented a sparse matrix library that we connected to the Lisp interpreter, and turned this into basically a neural net simulator. It turns out no one else had things like this, and that gave us complete superpowers. So the reason why, when a few months later I left to do a postdoc in the University of Toronto, and I was able to do things like implement convolutional nets, is because we had this system, and it gave us an incredible amount of flexibility. So one thing that's very important, I think, for us to learn now, which is that building your own tools give you superpowers that other people don't have. And I remember that lesson, and this is the reason why there is a big push now for basically open sourcing all your tools, because it allows a lot of people in the community to essentially build on your own research. So one problem we had with this is that this was before the days of the internet and before the day of open source, and for various reasons we could not open source this software. And the result is that for a very long time, for almost 20 years, we were the only one who basically were able to train convolutional nets. Not really only the only one. There were like other groups who had implemented their own things, but but it didn't have the impact that it could have because the tools had not been distributed, essentially. And by the time we distributed them, nobody was interested in it. So when I was in Toronto, I started experimenting with convolutional nets because this was kind of the logical extension, training with backprop using shared weights, like, being inspired by the locally connected sort of Hubel-Weasel type architectures. We didn't have data sets, so I had to draw, characters by, with a mouse and things like this. And then I was recruited by Bell Labs. So turns out the people I met in Les Ouches, I'd started a group at Bell Labs to work on hardware neural nets, and they apparently were impressed by what I talked about at that meeting, and they invited me for an interview, and then they offered me a job. And I wanted to come back to France, as I said earlier, but I said, my wife wanted to come back to France. We had 2 young children. And I told her, we're only going to go there for like a year or 2. But I was incredibly impressed by the place because it was this gigantic building with 5,000 people in it. 300 or so of them were research scientists. And this is where the whole organization was led by a Nobel Prize winner, Arno Penzias, who had discovered the background radiation of the universe. I mean, this was an incredibly impressive place. When I interviewed there, they showed me various labs where they were mostly physics lab, right? And every single one of them, I'd read about them in like Scientific American or in La Recherche, which, so I was incredibly impressed to be there. So I said, I have to spend at least a year or 2 to learn how to do research there. And I stayed much more than that. So this is my boss, Larry Jackal, here at the top left. This is on a boating trip that we took together. And he built that group where, and you see kind of a later version of the group here at the bottom with Léon Boutou. You can recognize Vladimir Vatnik, Patrick Hafner, various other people, Rico Zato, Hans-Peter Graf, John Denker, who's the guy in the white shirt. This group was incredibly productive. So it built special purpose hardware for neural nets, and then we quickly realized that the interesting thing to work on was actually learning algorithms rather than hardware, and things like convolutional nets. So they had a data set that they obtained from the US Postal Service, which was incredibly large for the time. It had something like 9,000 training samples, which was, unheard of, unbelievable. So I experimented, I already had the code for convolutional nets, which I had built in Toronto, and I kind of, trained the system on the data set. And within 2 months, I had the best results. And so that really sort of, quickly convinced everyone in that lab or almost everyone in that lab that, ConvNets was really kind of the way to go for image recognition. And pretty quickly, we kind of got associated with advanced development applied research group that, tried to kind of turn this into sort of a technological innovation and turn it into products. And that happened over the next 5 or 6 years, essentially. So, we all know about convolutional nets. There were various projects by some of my colleagues and some of which I participated in of actually building chips that could implement convolutional nets really quickly. The latest one being the ANA chip, which was completed in 1992 and was capable of the unbelievable speed at the time of 4 billion operations per second. But it used analog computation. So yeah, we could do convolutional nets. They were working amazingly well. That's a 30-year-old version of myself, and I can put a bunch of like a piece of paper under a camera, a video camera, hit a key, and we have this convolutional net code running on a special board that has a digital DSP, and you can recognize all kinds of characters and sort of you could do things that are very sort of unusual. So this was, around somewhere between 1991 and 1993. I can't exactly remember the date where we shot this video, but this was around 1991, I think. So, that kind of led to product developments, essentially. And I was, this was the first time, that I worked on anything that sort of really kind of made it to sort of practical use. So it's a good example of, advanced research with sort of long-term goal. This is Donnie Henderson, who was the engineer who put together the demo system, and Rich Howard, who was the lab director. And it actually made the news. There was an article in the New York Times about how Bell Labs, was capable of recognizing zip codes and stuff like that, and things like this. And And we came up, in the process of doing so, we came up with sort of the generalized concept of differentiable programming, which really is sort of the idea behind deep learning, right? So the idea that you can build an overall learning system by having modules that are predefined or you can define yourself that know how to propagate activations through them, compute the output from the input, but also know how to backpropagate gradient through them, essentially using an application of a chain rule. And the way you can build those systems is that you have some sort of object-oriented framework where you have classes for each of those modules, you assemble them in a graph, and then you get automatic differentiation by just reversing the graph essentially. So Léon Bottou actually originally came up with this idea, and he and I kind of implemented a system called SN2.x, which kind of implemented all of this, which was based on Lisp. It was a follower, kind of a spin-off of the first system SN that we built. Eventually, this was open source in 2002, but by that time, nobody was interested in neural nets. So very few people used that system because nobody wanted to learn Lisp by then. And certainly people were not interested in neural net that much anymore. But it was very similar. It was basically the ancestor of all the systems that you see now, PyTorch, TensorFlow, things like this, where you get automatic differentiation. Of course, there's all kinds of fantastic contributions from people in those domains, but the root of it really is SN and then Lush, which was the open source version. We came up with concepts like energy-based models and graph transformer networks, which I'm not going to go into, but build practical systems that could read checks. And by the end of the 1990s, one such system actually was recognizing something between 10 and 20% of all the checks in the US. So this was really kind of a first large-scale application of deep learning, generally speaking, if you want. Or there were many applications of like smaller neural nets, in various industries. But this was really kind of the first, really sort of large neural net, if you want. So quickly we realized that we could apply convolutional nets not just to single objects, but basically apply it with a sliding window, so that we could do things like object detection, and also recognize multiple characters without having to pre-segment them. So this became really an important concept because once it became time to apply convolutional nets to natural images, in natural images, it's very difficult to separate an object from its background, right? I mean, one of the big difficulty of computer vision is to actually recognize an object in its context without having to separate it, segment it beforehand. So that turned out to be a really good idea, that you could just slide a window of this convolutional net over an input, which turned out to be very cheap to do because you just extend the convolutions, and that way recognize multiple objects without segmentations. So I briefly went back to France in 1991. I was working actually at the central research lab of Thomson CSF. It's not called that anymore, but and worked on phase detection. And we built one of those sliding window idea to build a phase detector. We published this in 1993. And the paper was completely ignored. And there were papers 10 years later that kind of recycled this idea for detection. But this was too early, right? It was kind of too ahead of its time. Now, here's what happened, though. There was an interesting dynamics that happened within our lab, which is that in the office almost next to mine was Vladimir Vapnik. He joined Bell Labs about a year after I did. And he was working on learning theory, and he had come up with this theory of generalization based on, what he now calls the statistical learning theory, based, with concepts like the Vapnik-Chamonix dimension and things like this. And the theory was telling us a lot of things about what's possible or not possible with learning machines, and that sort of conceptually helped us a lot, kind of frame everything we were working on. But there was a limited role for practical role for theory, in the sense that none of the theory ever produced kind of practical ways of predicting the generalization ability of a system. It's fantastic at the conceptual level, but not at the practical level. People do cross-validation. They don't actually, predict the generalization using formulas from learning theory. And Vapnik was actually very, very skeptical about neural nets because he did not understand the advantage of having multiple layers. Okay, it's an advantage when you write mathematics. You want to represent functions. It doesn't matter if you have layers or not, right? It's just a function. And so he didn't see the advantage of having multiple layers. And in fact, he thought that actually hurt because if you build a system that basically only has one layer of trainable parameters, the function you're optimizing is convex. You can prove things. You can maximize the margin. You can, prove bounds on the generalization. And so there's a lot more theory you can do. And whereas with neural nets, you cannot do the theory. So he was very critical of neural nets. And I was very skeptical of support vector machines because I thought this was never going to be a solution to computer vision. And so Larry Jekyll, who was our boss, essentially our lab director, wrote this bet. He says, so he made a bet with Vladimir. And he said, Jekyll bets one fancy dinner that by March 14, 2000, this was in 1995, people will understand quantitatively why big neural nets working on large databases are not so bad. Because they were working pretty well. But by 1995, people started losing interest in this. They were working on kernel machines, support vector machines, which were invented by Isabelle Guillon, Bernard Bozer, and Vladimir Vapnik, who are in our lab. They were in our lab. And then Vapnik bets one fancy dinner that Jekyll is wrong. But if Vapnik figures out the bounds and conditions, then Vapnik still wins the bet. So this was a thinly veiled attempt by Larry to basically convince Vladimir that he should work on the theory of neural nets, basically. That didn't happen. By 2000, actually, people were starting to get interested in neural nets again, at least a few people, and they were clearly working very well for a lot of applications. So Vapnik lost that bet. And then Vapnik had another bet. Vapnik bets one fancy dinner that by March 14, 2005, no one in his right mind will use neural nets that are essentially like those used in 1995. Jekyll bets one fancy dinner that Vapnik is wrong. This was signed by Vapnik, me, Larry Jekyll, and I was the witness. So we actually had a dinner in 2005, and Larry Jekyll lost that part, and Vladimir Vapnik lost the second part, because by 2005 there was a revival of neural nets, and people were starting to use them again. So, so that shows you that sometimes theory can mislead you in some ways. And in fact, my beef with kernel methods, which I found was a fascinating technique, but was not kind of solving any problem I was interested in. Is that kernel methods are basically, kind of glorified template matchers, essentially. They match the input vector to a bunch of templates that are the sample from your training set, and then you get scores for how well they match, and then you compute a linear combination of those scores. And that's basically, a little bit better than k-nearest neighbor, but not much. So you're not going to be able to, recognize natural images with invariant properties using something like this, unless you build those invariance properties into the feature extractor. But I thought convolutional nets were a much better way of learning those features because you could learn them. So the impact of this department, the Adaptive System Research Department, that existed between 1985 roughly and 1995, led by Larry Jekyll, was things like convolutional nets, like some of the first neural net chips, the final incarnation of statistical learning theory, empirical risk minimization, structural risk minimization, VC dimension, support vector machine and kernel methods, regularization methods of various kinds, applications of boosting, practical handwriting recognition system, check reader, etc. I mean, it had a huge impact. But that didn't stop the community from abandoning neural nets in the mid-90s. And one can ask, we can ask ourselves why. Why is it that, despite the fact that there were those success, the community kind of moved away from it? Part of it was computational resources that were very demanding for neural nets. Part of it was the tools I was telling you about. We were one of the only groups who had the tools to basically train neural nets in an efficient way, things like convolutional nets. And people just did not want to invest the time to kind of build those tools, and we could not release them in open source. And so, because the tools were not available, people were not interested. And furthermore, they didn't even necessarily believe our results because they could not reproduce them. Data was scarce. There was no internet. It was just the early days, and so there were no like big data sets you can use. And so that, the tools that we have shape the direction of the research. And so that taught me a lesson, which is that, if you want an area of research to be pursued, if you want to have an impact on that area of research, you have to make everything available so everyone else can reproduce it. If you keep some of the tools to yourself, here it's not because we wanted to give them to ourselves, because the lawyers of AT&T wanted, made it difficult for us to release it. Then you end up being kind of intellectually isolated, and you do not have the impact that you could have had. There are famous examples of this throughout history. So the result of the community, losing interest in neural nets is that it wasn't fun for me anymore, or for people like Clément Boutou and others. So we actually stopped working on machine learning and neural nets around 1996 until about 2001, and started working on other things like image compression. So I completely stopped working on neural nets. I wrote papers about stuff we did before in that period, but I basically stopped working on neural nets and machine learning in the late 90s. This was the group. So I became the head of the group. So I kind of had management duty, which kind of slowed down my research as well. This was my group at the end of the 2000s. Right. So there's a controversial proposition that I just made, which is, machine learning fell victim to the theoretical streetlight effect, which is that, machine learning started to get interested in things that has skewed mathematics attached to it, despite the fact that there were other models for which there is no such skewed mathematics, but which actually work better. And so the community somehow was able to dismiss the fact that those things were working better. I think it's a really interesting lesson because, we have a tendency, particularly in France, actually, to be hypnotized by, cute or brilliant mathematics, which is great, but not at the cost of ignoring kind of practical things for which we may not have the theory, but which may have, great practical consequences. And in fact, this is something that Noam Chomsky, still him again. Science is a bit like the joke about the drunk who is looking under a lamppost for a key, and he has lost on the other side of the street because that's where the light is. It has no other choice. So there's a bit of that phenomenon, I think, that occurred. And I'm showing this. So this is for those of you who are from France, you know this as being the L'Avion 3 of Clément Ader. You can see a reproduction of it at the Musée du CNAM in Paris. If you're not in Paris, I very much encourage you to go to that museum. It's a fantastic museum. And he had very little impact in the aviation, future aviation. His main impact was that he coined the word avion, which is the word for airplane in French and Portuguese and a couple other languages. But his impact on flight technology is actually very small, and it's for two reasons. The first one is that he was very secretive. So instead of sharing his results and his tools and sort of telling the world about his thing, he wanted to keep it secret. He only showed it to a few people, and as a result, a lot of people just didn't believe that his airplane actually flew. Just didn't believe him. And the second thing he did wrong was being hypnotized not by theory, but by biology. So he copied bats. He studied bats and copied bats and tried to copy all the details, including folding wings and things like this. And that was a mistake. So this is also something we have to be very careful of in the context of AI, which is, we can get inspiration from the brain. We can get inspiration from cognitive science, from psychology, but we don't want to get caught in the details of it, so that what we reproduce in our artifacts are the details that are irrelevant, in fact, to the overall thing. So, the big question is, what is the underlying properties of intelligence that the brain implements that we need to reproduce in artificial systems? But the details of how neurons do it is irrelevant. Like, for example, does it matter that neurons spike? Should simulated neurons also have spikes, like current ones don't? But there's a lot of people working on spiking neurons, spiking neural nets. So that also asks the question of, is deep learning, so first of all, deep learning is an engineering science. It's not a natural science, in the sense that, we come up with new artifacts, and then the analytics of the science, is to kind of study their property and optimize them. But coming up with new ideas is really engineering. Sort of the creative act of coming up with a new artifact is engineering. The theory comes after the invention of the artifact. And even in science, even in natural science, empiricism works. So I'm not an advocate of pure empiricism, obviously, but empiricism sometimes takes us places where pure theory would not. And sometimes theory takes us to places where empiricism could not. And so there's always this interaction between the two things that we need to maintain. And people have been sort of criticizing deep learning as being some sort of alchemy because people use lots of GPUs and experiment with all kinds of different things without really understanding how it works. I mean, it's a perfectly fine way of doing science. A lot of people have been doing this in chemistry and biology and certainly drug design and things like this for decades, for centuries. So this is not necessarily a bad thing. You have to do it right. So software and hardware limitations limit the research directions that you allow yourself to work on. So then in the early 2000s, I switched to academia, becoming a professor. There was basically no space in industry anymore for fundamental research, and kind of restarting a program to work on machine learning and basically kind of trying to reconvince the community that neural nets actually were not a bad idea. And in this, I got together with my friends Jeffrey Hinton and Yann, who were also kind of in the same situation I was, kind of trying to convince people that neural nets actually worked. So I started doing some experiments, to show A/B comparisons between things like supervector machines or other methods, classical methods, with things like convolutional nets for recognizing complex shapes with invariants, and showed that it does work a lot better if you use convolutional nets. You can't use SVMs unless you hardwire features. And so I was kind of advocating for the idea of learning features, and then had other work on phase detection and image segmentation, and which was picked up by my friend Sebastian Song, who was at MIT at the time. He used convolutional nets. This was in the late 2000s to segment brain tissues so that he could reconstruct the diagram, the wiring diagram of a piece of brain tissue, if you want, to figure out how the brain of a mouse or a fly can work. And that actually became an entire subfield now. So there's a lot of people working on this kind of techniques. They all use convolutional nets, and that started before convolutional nets were cool. Also worked on robotics, using imitation learning, using convolutional nets to get a little truck robot to drive itself, or using a bigger robot to drive itself. This was a DARPA project in the late 2000s. Using convolutional nets to do semantic segmentation and things like that, and that worked pretty well. And robots that could drive themselves. But this was before deep learning was cool, and so none of this was really kind of had any impact, if you want, in for example, the computer vision community, or very little impact in the robotics community. It was difficult to reproduce, even though then our tool were open source, but the community was not interested in neural nets, and they didn't want to invest the time to kind of learn them. So we worked on semantic segmentation. So this is an interesting story. Some of you know that story, I know, which was to apply convolutional net to semantic segmentation with natural images. Some data sets kind of started popping up at the time, and we had really good results there. Beat other system, and had a system that worked really well, and submitted this to CVPR. And the paper this was in 2011, and the paper was rejected because essentially the reviewers didn't know what a convolutional net was, and it did not believe that a method they never heard of actually could work so well, essentially. But it did work well. So let's see, I'm out of time. So there was the deep learning revolution, which we all know about, and we had a kind of an explosion of things that happened. But I want to say two things. The first thing I want to say is that the artifacts that we invent, we generally invent them way before we figure out the theory for them. So for example, the steam engine was invented somewhere at the end of the 17th century, early 18th century, but thermodynamics was not actually devised until about 100 years later to really explain. And thermodynamics, became like the foundation of, much of physics. And you can make a list of those things. It's the same thing. Optics, electronics, etc. So I think we're in a bit of that situation now today that we have an artifact, but we don't have a complete theory for it, and we need to figure out the theory of intelligence and learning, essentially. I want to say just one word about yes. I should stop, right?
Can you keep some time for question?
Yes. Okay. Yeah, because we're short. Okay, I'm going to stop here, actually.
Oh, but you have a few minutes if you want before.
No, it's okay.
Okay, so thank you. I'm sorry. I don't.
We can do it. I could stop anywhere. We can do it through questions, actually.
Okay, so thank you very much. So we will. There are a lot of questions on the chat. So I will first ask Jean-Luc Bella from Nokia Bell Labs to ask the first one. He represents all the partners of Prairies, and during this time I will have a look on the question. So Jean-Luc, if you can come.
Hello, do
Thank
you
you.
hear me?
Yes, perfect.
Okay, so thanks a lot, Yann. So last time we met together, it was the PRAIRIE event in Paris. So
sorry, I have a hard time understanding you. I can't hear very well. You're.
You can hear me?
I can see you, but I can't hear you. I can't understand. I can hear you speaking, but I can't understand you.
Maybe my question, I will be short. My question is, what is, according to you, the structure of the back propagation? In fact, what you...
Okay.
Yeah.
That's a very good question. So this was the little part of my talk that I didn't get to. But I think the idea that we're going to build AI systems by assembling functional blocks that are differentiable, and we're going to train them using gradient-based learning, this is an idea that is not going away. This idea is going to be with us for a long time. So I think the future of AI includes this idea of basically, deep learning, essentially, right? Gradient-based learning applied to complex architectures. What this architecture will look like and the type of learning that we will eventually use, that's the question. Can we make those systems learn without requiring as much label data as they currently require, using self-supervised learning, for example, which is the topic of my other talk that you might find on YouTube. Or, can we get machines to reason? So these are the main two issues, I think, that we need to solve to make progress. Getting machines to learn by observation, by watching YouTube videos, for example, as opposed to being trained for a particular task, so that we can get them to learn some level of common sense. That's the first thing. And then the second thing is devising architectures that will allow machine to reason as opposed to just like perceive, right? Current deep learning systems basically, have a fixed number of steps, right? But for reasoning, you want something that's kind of more iterative. So that's the two big questions, I think, for the future of AI. But deep learning is part of the solution.
Okay, thanks a lot. Maybe I leave this time for other questions.
Thank you, Jean-Luc. Bye. So I will resume the other question. So people are asking if they will have the presentation, so there will be a replay. I can answer myself. So next question with a lot of vote is about career. Do you think that that it is possible now to have a career like yours in France today?
So it's easier today than it was when I was there, perhaps. Not easier, but at least there are opportunities. So when I came out of PhD, I had the choice between research position in industry. There were very few research labs in France that actually were doing sort of fundamental advanced research. It was CNET, from France Telecom. It was the Thomson Central Research Lab at the time. Philips also had a research lab. Most of those labs actually closed down over the next, the following 5 or 10 years. IBM also had a lab. It was very applied. So industry was not that great in France and in Europe generally. It's better now because you have labs, from Facebook and Google that are established in Europe. So now there are more opportunities where you can do really sort of advanced fundamental research. It's good. And then public research was very difficult, right? I mean, it's kind of an obstacle course to get into a public research position. I wasn't coming out of, École Normale or École Polytechnique, right? I was coming from a small school, so that gave me a disadvantage right there. I was working on a domain that wasn't like a major thing that people were interested in. It was a bit of a maverick, right? So it's not clear I had a place anywhere in France where I could, someone would give me a job. And also, I already had a baby, and I had to support a family, and it's very difficult to do, in the Paris area with, a salary from CNRS or something like that. So, I had to go abroad, first because I was offered a job where I was paid like 3 or 4 times what I would have paid in France, and working with people that I really wanted to work with, and with means. Give you an example. When I was hired at Bell Labs, there was this new type of computer that came out from Sun Microsystem called the Sun 4. And when I was in Toronto, there was a Sun 4 for the entire department. And when I got at Bell Labs, just a few months before I got there, my boss, Larry Jekyll, said, we want to buy a computer for you that will arrive before you come. What do you want? I said, well, here we have a Sun 4. That would be great. He bought a Sun 4, and I realized when I got at Bell Labs that I had a Sun 4 for myself. Like this would never have happened anywhere else, not in academia in the US, absolutely nowhere in Europe. This is, so if you want, to give people the means to succeed, right, you have to pay them well, so you attract the best people, so you motivate them to go into the career, first of all, and you have to give them a lot of freedom, and you have to give them the means, the physical means, essentially, resources for them to succeed. That's what I tried to reproduce at FAIR. When I created the Facebook AI research, that's what I said. We need to do open research. We need to give freedom to people. We need to do, we open source everything we do, so our tools have an impact. And we need to have enough resources so that people can succeed. And we need to pay people well.
So, completely different question. So I will group 2 questions to try to take more. One from Aina Space. I hope I pronounce well the name. It seems that you started your research in neural network when it was quite a niche. Do you see any comparable niche research areas today that might be worth pursuing? And another one, a little bit different, but also quite technical. Do you think that the future of machine learning only lies in deep learning?
Yeah, right. So it was not a niche; it was a cult. It was, it was only crazy people who were working on it, right? Because there was the history of the perceptron. Like no one in their right mind. So if I had followed the normal route of doing a PhD with someone who tells me what to work on, I would never have worked on neural nets because no one would have ever proposed this to me. Instead, I knew I wanted to work on neural net. I got some sort of fellowship from my engineering school, from ACA. Actually, they funded my PhD for some reason, and I'm very thankful. And I went to a professor who said, I can't advise you, I can't sign the papers, but I don't work in this area, but I'll let you do whatever you want. So that's the kind of niche that it was. It wasn't a field at all. Now, are there such niches today? It's difficult to say. I mean, what I'd love is for someone listening to this who is a student at a school right now, not starting a PhD yet, to basically tell me everything you've done is complete bullshit, and you should here is this other way of doing things that I think is much better. And I really hope that this will happen, pretty soon, because that's how we make progress, right? But do I believe that things like deep learning will be part of the future of AI? Yes, absolutely. So maybe I'm wrong about this. Prove me wrong. I think this idea, again, as I said to answer the previous question, assembling learning systems. So first of all, assembling artificial intelligence systems by training them, I think is important. I think they will be trained through gradient-based learning. So they will be trained, there will be architectures that are differentiable, and there will be deep learning involved. It may not be neural nets. It could be, something else, differentiable programming, as it is called now. It will probably involve something like self-supervised learning. So not just reinforcement learning or supervised learning, because that's the way humans and animals learn. and it will involve something that, architectures that allow reasoning. So that's my idea of the future. I may be wrong.
Okay, thank you. Another group of 2 questions, not exactly on the same, but more on ethics and regulations. And one from Julien Tegny. Do you think there is enough research discussion about ethics in the AI field? What is your view on the recent case with Google and its AI ethics team? And another one, sorry, I just come from, sorry, I lose it.
Well, I can
yes,
I can answer the first 2 already. I mean, AI ethics. So the ethics of using computerized decision systems. This is not specific to AI, right? I mean, this is in general when we use computers to help people make decisions or make decisions that have a big impact on people's life. You have to study the consequences of this before you deploy the system. So this is not specifically an AI ethics question. It's a question of the ethics of applying computerized decision systems. Whether they are trained, whether they are intelligent or not is not the relevant question there. Now there are specific questions that are due to machine learning systems, right? So if you train a machine learning system with biased data, it's going to reproduce the bias, sometimes amplify it, and it's going to amplify it. For example, if you train a face recognition system with a representative population of the sample of the French population, it's not going to work very well for Black people because if your sample is representative, there's just a relatively small number of Black people, and so your system will, your deep learning system will not pay as much attention to that part of the sample as to the dominant one. This is a bias that humans themselves are full victim of. People are better at recognizing people from ethnic groups that they grew up with. It has nothing to do with their own skin color, but it has to do with people they grew up with. So this is important things that you need to know, right? If you want to train a face recognition system that works as well for every category of people, you have to know this in advance. You have to correct you have to actually bias the data so that your system will actually learn properly. You don't have to debias it, you have to bias it to make it run properly. So there's a lot of questions. So the question of whether there should be more research on ethics or not, I can't answer that question. I can tell you that every important research group on AI has an AI ethics group, and is devoting a lot of attention to it, and that is true for Facebook and Google, etc. Now, I'm not going to comment on what happened at Google because it's their problem to deal with, and it's a difficult issue that where we don't know the story really. We only know the story that has been told by the people who have spoken, and Google has not spoken.
Okay,
that's what I can say.
Another one from Eileen Chivo. Again, sorry if I misspell your name. How are you looking at current policies proposal for AI regulation being deployed in the Europe by organizations like OECD, and some other one? Does the field need those rules? Does they make sense for engineers? Or do you expect there could be some gaps and so on?
Yeah. So I mean, I don't know what specific regulation you're talking about. There's different types of regulation, right? There's regulations about privacy protection, about things like this, about where data can reside, can it be stored on servers outside of a country, things like that, right? There's regulation about Facebook, for example, does a lot of content filtering, right? They filter, Facebook filters, and this, by the way, is entirely built around deep learning, right? So things like filtering hate speech, violent speech, terrorist propaganda, nudity, things like this that the content policy basically say you shouldn't do. Those are mostly filtered by automatic systems. It's very far from perfect. There is a relatively small number of false negatives now, but a pretty large number of false positives. So, the technology is not where we want it. Now, who decides what hate speech is? So right now, Facebook has to decide, by itself what the content policy, what's the definition of hate speech. This is not something that is connected with AI, by the way, right? The AI is just the way to enforce it, but the way to decide the policy has nothing to do with AI. But Facebook has said, to various governments, like, help us, like, tell us what is appropriate content online, because we don't think that we have the legitimacy to decide what is hate speech or what is not hate speech. So right now we have to set up our own policies, but eventually we'd like you to tell us. We don't want to do it ourselves. Now there are, so I think more broadly though, I don't think AI in itself should be regulated. I think applications of AI should be regulated. So if you're going to apply AI to autonomous driving, then there should be regulations about how safe that should be, right? Like, procedures for how to test it, for how to kind of decide whether to put it on the market and things like this. It's kind of like, clinical trials for drugs, testing for cars. They need to get a stamp of approval from the government before you can sell a car, or just about anything for that matter. So I think there needs to be standards for that, for products that have AI inside, but I don't think it's AI regulation. It's regulation of the product that you're putting out.
Yeah. So I suggest that we come back to more technical things and the future of AI with a question of Pablo Mirales. What is your take on the role of causality in neural network and artificial intelligence training? Do you agree that detecting and exploiting cause-effect patterns will be required to overcome the current shortcomings from ML models?
Well, so they will certainly cover some shortcomings, but not all shortcomings, okay? The main, so let me tell you about, so I told you about the two challenges for AI. The first one is to learn without labels, and the second one is to learn to reason. And causality will help with both, but will particularly help with the first one. Let me tell you why. Why is it that a human can learn to drive a car in about 20 hours of practice with very little supervision without essentially crashing ever? Whereas if you were to take a blank reinforcement learning system and put it on a simulated car and have it drive the car, the system will have to drive for hundreds of thousands of hours and crash tens of thousands of times before it even figures out that how to stay on the road. So what's the difference? The difference is that humans have a very, very accurate model of how the world works. We know that when we turn the wheel in a particular way, the car is going to go on one side, and if there is a cliff next to it, the car is going to run off the cliff. Nothing good is going to come out of it. We don't need to try it to know the result, because we have a good intuitive model of physics and how the world works. So that allows us to predict in advance what's going to happen as a consequence of our actions, right? So we have this model of the world. It's basically the entire front part of our brain. That's what it does, okay? It allows us to predict what's going to happen, predict what we can't directly observe. Either predict the future, predict the past from the present, predict occluded parts, like you can see the back of my head, but you have a good guess what it looks like. Our brain is a prediction engine, and it trains itself to predict, and part of it is that it can predict the future state of the world that would occur as a consequence of our actions. So that allows us to plan. That allows us to reason and to plan ahead. That allows us to simulate in our head what would happen if we take a course of action and then optimize the sequence of actions to arrive at a particular goal. That's how we solve problems. And reasoning basically is a form of that, right? Almost all of reasoning could be kind of cast into that framework. So I think the big challenge for AI is, how do we get machines to learn such a model of the world? Learn that, if I hold an object in my hand and I let it go, it's going to fall. Babies learn this. Human babies learn this by the age of 9 months. It takes them about 9 months to figure out that gravity is a thing. Okay, it took all of us about 9 months. How do we learn this? We learn this mostly by observation. We don't interact with objects very much when we are very little. By the age of 9 months we do, but 2 or 3 months we don't. We have almost no effect on the world. So how is it that we can just observe the world and figure out how it works, build predictive models of the world by observation. That's the main thing we need to, that's the main problem I'm interested in. That's what all of my research is centered on, essentially, okay? Now, if you want a model that is good at predicting what the effect on the world is going to be when you take an action, you need a causal model. That's actually what causality is all about, right? So you try something, you see the effect, and then you deduce causality from this. But humans are not so great at causal inference. We attribute a lot of causes to things that don't have any. We invent gods for things that we don't explain, right? That's not a good causal inference.
Okay, a group of questions, more maybe for students. Three question. Why PhD is not valued in France as it is in the US and other countries? Another one, do you have one advice for ML students wanting to become researchers? And the last one, do you think machine learning programs, undergrad and masters in France, are comparable to those in Anglo-Saxon university? Or do you think France is still trailing on that front?
No, I think the opposite. So programs in France, like the MVA, for example, the masters in vision apprentissage, I think it's probably one of the best programs in the world. People coming out of this are extremely well trained, much better than any undergrad from any American university. So they know a lot more. I mean, there's no question about it. So if you're going to do your undergraduate studies, you might as well do them in France. I mean, I think the French educational system for undergraduate studies is really good. Now, PhD is a different story. So the advantage of doing a PhD in France is that, you do 2 years of master's and then you do 3 years of PhD, and where you concentrate on research. Whereas if you do it in the US or even in the UK or in Canada or many other countries, you don't do a master's, right? You go directly to PhD, but now the PhD is 5 years. And it's very tough to get in. It's extremely selective because there is a high value associated with PhD in such countries, which is much higher than it is in France. So that's an issue. Now that's changing though. I think the PhD is more and more valued in France for various reasons, partly because of labs like Google and Facebook who would hire top people with a PhD and things like that. So I think there is a big advantage to doing a PhD. It's internationally recognized. I think the reason why the PhD was not so recognized in the past in France is that is the grandes écoles, right? People care more about the undergraduate school you went to than your sort of research accomplishments, and it's the entire kind of promotion system in France kind of was designed this way. It's changing, fortunately. So I would encourage everyone who is really interested in research to do a PhD.
Nice. Another question, maybe a last one or maybe one or two more. What do you think of current research publishing culture? Have you felt an increase in the pressure to release publication in your lifetime? If you have, what do you think of it?
Yeah, I was joking with a colleague once that, if I look at the publications I had when I finished my PhD, which was like, 3 publications in sort of obscure venues, 2 of them were in French. I would not, I would not get a job, right, anywhere. I would certainly not accept myself, my undergrad self, as a PhD student in my own PhD program. Okay, so things have changed, right? Now there's a lot more demand on for publications. I think it's good because, it's good and bad, but it's good in many ways because what it indicates is that people are much more communicative than they used to be, right? You used to kind of do your research and, would eventually write about it, but you would have a hard time disseminating your ideas. But now with archive, with, the communication that we have on the internet, social networks, etc., it's much easier to disseminate ideas, and good ideas get picked up. And so it's much easier now, I think, for a very talented, bright person who's isolated, in sort of remote corner of the world, to actually have their idea being recognized, because you just put, you don't know how to write a paper, so you're not going to get a paper accepted at NORB or ICML or CVPR. if you don't have anyone to kind of really advise you on how to do this. But you can write something and either write a piece of open source code and contribute to it, or put a thing on archive, and then whenever someone else get the same idea, you can point to your thing and say, oh, I thought about the same thing before. Maybe it wasn't perfect. Like if you look at my early papers, it's really embarrassing. Okay, they were horribly badly written. The scientific methodology was terrible. I mean, like they're really embarrassing. But what that tells you is it's okay. You don't have to be perfect. And so I like this idea that the fast, high bandwidth communication in science is more noisy, but makes the whole field progress faster and is a better way of identifying talent than it was, back when I was a student.
Maybe in the same idea of pressure, a question of Pierre Lejeune. Do you think it is still possible for small teams, research groups to compete with huge AI labs like FAIR, DeepMind, and so on?
Sure, absolutely, yeah. I mean, I have two research groups, right? One at Facebook, a small research group with 3 postdocs and 1 engineer. It's not that big for my own research projects, right? Or theirs, more or less. And then I have a separate group at NYU with 4 students and 2 postdocs, and I see them as very complementary. So I don't think research in industry completely overtakes research in academia, or for small groups even in industry. I think you have to be smart about identifying kind of good projects to work on. So if you have, so let me tell you an interesting story in that dimension. Back in 2014 or 15, there was this paper by Ilya Sutskever published at NIPS. It was still called NIPS at the time, where he showed that you could train some gigantic multi-layer LSTM to do language translation, and you could get results that were basically comparable with more classical systems. And that really kind of opened the eyes of people that you could use neural nets for translation. Now, only a few months later, I mean, this was a gigantic model that basically only Google and perhaps Facebook could build. A few months later, Dmitry Badanao, Kyung-Young Cho, who is now a colleague at NYU, and Yoshua Benjo came up with this idea of attention. They said, like, you can use this multiplicative interaction so that you build a translation system so that when it comes time to generate a word in the target language, you pay attention to the corresponding word in the input sentence, and that's kind of dynamically determined by, a gating mechanism, essentially, right? And attention, that they call attention. That really interested a lot of people, because now you can do translation with decent performance with a network that was kind of decent size and you could train in a university environment. That was picked up by Chris Manning's group at Stanford. So he built a fairly large-scale version of this, and he participated in the WMT competition, which was the translation competition, and won with that idea. Immediately, every single industrial group started saying, this is what we need to do now. So they, picked up the idea of attention-based neural nets for translation, and every single translation systems, from Facebook, Google, Microsoft, and everybody else was based on that idea. So now that the performance of the translation system went up by a big chunk, and Yoshua Benjo told his students and postdocs, we're not going to work on translation anymore. Okay, stop working on translation. It's not worth it, because we're not going to be able to compete with industry now that they picked up our idea. But they had a huge impact, right? They came up with the idea that industry picked up and kind of run with. But once industry picked it up, there was no way, right, academic groups could compete with it. I mean, there were similar stories, happening 10, 20 years ago in speech recognition, handwriting recognition, OCR. I mean, it's a natural, lifetime process, if you want, of a set of ideas. So there's a lot of things, maybe that are niche now today, corners of deep learning and things like that, where, we need good ideas, and the good ideas are going to come from academia at least as much as from industry.
So there was a several question about GPT-3. So if we merge all the question, what is your opinion about GPT-3? This is not a small group. This is a very large project with a lot of funds and so on.
Right. Okay. So there's good things and bad things about GPT-3. What it shows is what happens. Is there sort of any emergent phenomenon that occurs when you scale up fairly traditional deep learning systems, right? You just make them bigger, right? Train them on more data, on more, machines in parallel. Do you observe something emergent? And what you see with not just GPT-3, but BERT and Roberta and XLMR that came from Facebook and things like this, is that yes, it seems that if you train very large transformer-like neural nets in a self-supervised manner to basically predict missing words in a text, there's a lot more that the system can do than you would expect, right? They seem to be acquiring a very shallow version of common sense, okay? It's not common sense in the sense that, they will know that, if I say a sentence, the blank chases the blank in the savannah, that the first blank is probably cheetah or lion, and then the second blank is probably antelope or wildebeest or something, right? Because you know the context, and you can learn this from text statistics. And so GPT-3 is a good demonstration of how far you can go in that direction. And you can go surprisingly far. But there is an underlying, I wouldn't say assumption or idea, which is that we can achieve sort of human-level AI or common sense just by scaling up kind of existing methods. And that I absolutely do not believe is true. So we're not going to get machines that learn common sense by, training gigantic networks to predict missing words in text. And it's because most of human knowledge does not reside in text. So if I tell you, for example, I'm going to put, this water bottle on the table that is right next to me, and I'm going to push the table so it slides on the ground, on the floor. Where is the bottle going to be? You can tell, because you have common sense, that the bottle is moving with the table because it's sitting on it, right? I can almost guarantee that GPT-3 doesn't know about this. Okay, there is no text that explicitly says when an object is laying on another one. When you push the first object, the second one moves with it. This is something you learn by experience of the real world, by observation in the first few months of life. Same with object permanence and gravity and all those things, right? And most of our knowledge is of that type. The type of knowledge that we have that is linguistic, that is, we can convey using language, is tiny. We think it's all of it because, as humans, we're so dependent on language. But linguistic knowledge is a tiny, tiny portion of human knowledge. And so we're not going to have common sense just by training machines to learn to predict text.
So thank you. A very last one from Aziz Fouché. Do you think there is a race towards model performance at the detriment of model interpretability? If so, do you think there is a way to conciliate both? Okay,
that's an interesting question, because I actually don't believe that interpretability is important. Okay, so I don't think it's a trade-off. I think we should go for the best models that do the best prediction, and interpretability is essentially useless. So I've been in that situation many times where I would talk to someone who is interested in using, machine learning for a particular application. Let's say an economist, okay, to take a random example, or biologist, or linguist. And you come to them a few months later. They give you some data set, and you come to them several months later, and you say, well, they look at you in the eye, when they meet with you, and you say, oh, but the model has to be, interpretable, explainable. Otherwise, it's useless to us. You don't believe them, and so you come back to them with two models: one that actually works well, but is some big giant neural net that is not explainable, and a simple model, like logistic regression or something that is explainable but doesn't work as well. And then you ask them, which one do you want? Okay, and depending on what their motivation is, if they want to write a paper, maybe they want the explainable one. If they want to write a paper about economics, maybe they want the explainable one. But then they'll turn around and say, oh, we can predict, prices now, so maybe we should do a startup. And now you ask them, okay, so which model do you want now? Do you want the one that predicts, or do you want the one that is explainable? Every single time they will take the one that predicts. Every single time. They don't actually care about explainability. No one actually cares about explainability. No one. Except when the decision to be made is an input to a human decision. So there you need calibrated scores, also known as probabilities. And you might need some explainability because, you know, it's a decision of justice or it's a, you know, a medical thing, and, you know, it might be useful to know why the decision was made this way. So there you might need explainability. But the proportion of applications for which that's required is absolutely minuscule, and in very narrow domains. So explainability is not that useful in the end.
Okay, so I want to thank you for being here today. I will read the last question that is not for you, but again me, from Amol Mayurkar, who said, if his time permits, please allow him to finish his talk. So I stop you, I'm sorry. We have only 2 or 3 people in the world who have witnessed the birth of AI. So I apologize, and I promise them that we will invite you next time for a second episode and the end of your talk. So thank you again, Yann.
The other talk is, you know, the end of the talk is more about, like, you know, this idea of self-supervised learning, etc. There are versions of this talk that you can find on YouTube that I gave. So I thought I would give a different talk this time around because you can watch those talks on YouTube. You know, I would talk about the history and the epistemology of AI and machine learning rather than my personal experience, because this is really the theme of that meeting. So my apology for taking so long and, you know, not actually going through the entire talk, which I'm, you know.
But we will invite you another time.
Okay, all right.
Thank you very much. Thank you, everybody. Thank you also to France Digital to be here with us. And we will see you next time on April 7. So bye.
All right. Thank you. Bye-bye.